Pulse is essentially the rhythmic reflection of your heart's activity, specifically one beat or one systole of the heart. In other words, it corresponds to a single cardiac cycle, which is a full cycle of systole and diastole, a full cycle of pumping and filling. Although pulses exist in veins within the systemic circuit, they're way too far from the heart, from the pump, to be easily detected. And this is why we measure pulses in arteries instead. Arteries, being closer to the heart, are where you can actually feel that rhythmic pulsing. And the closer the artery is to the heart, the stronger and more pronounced the pulse will feel. So take a moment to visualize this. If you were to look at a diagram like this, you'd see the heart located centrally. And as blood travels away from the heart to different parts of the body, the distance impacts the strength of that pulse, right? Just like a noise, the farther away you are, the weaker the noise is. For instance, let's consider the femoral artery, which is located on your thigh. As the aorta descends from the heart, it branches off to supply to major organs like the kidney, and then it continues down to feed the femoral artery, pretty big artery. And this large artery delivers blood to your lower leg, or legs, plural, if you're talking about both of them. I'm just talking about one, right? And your legs actually bear a lot of your body's weight. So because your legs have more muscle mass compared to your arms, the femoral artery carries a larger volume of blood. Personally, I prefer checking the carotid artery for pulse. That's the one in the neck to detect a pulse. It's closer to the heart and it offers a more strong or reliable signal. But if you want to detect your radial pulse, which is the one that's normally used, you can place two fingers on the radial side, the thumb side of your wrist, and you can use light pressure and focus on like the thinnest area of the skin. When recording your pulse, there are a couple methods. You could count the pulse for 15 seconds, multiply by 4. You could count it for 30 seconds, multiply by 2. Or you could give your patient a full minute of your time and count their pulse for 60 seconds. The number of pulses per minute equals your heart rate, which is measured in beats per minute. And that corresponds to the number of cardiac cycles per minute, right? Right, one round of pumping and filling. So this measurement, it gives me an idea of how many of these cardiac cycles you're having. And then I can use this number, the heart rate, to make some calculations and some estimates about the amount of blood that you are moving. First, we obtain stroke volume from a source. It's not something that you measure. Stroke volume for age, height, weight, gender, and all of that have been estimated from cadavers. So we're going to use a pretty average stroke volume for an adult, which is 70 milliliters. That's not a lot. It's like a little bit more than half a stick of butter melted. Everything to me is in terms of sticks of butter because a lot of us are familiar with that. Anyway, stroke volume is the amount of blood that's leaving a ventricle in one cardiac cycle. Don't forget, we consider stroke volume for the right ventricle and the left ventricle, which it should be the same. Cardiac output is the amount of blood that is leaving a ventricle in 1 minute. In order to calculate cardiac output, I need to know how many cardiac cycles somebody's having in 1 minute. And I also need to find a reference volume for how much blood they're putting out in one cardiac cycle. So this equation tells us that cardiac output rises with stroke volume. Cardiac output, it also lowers with stroke volume, which means that it's proportional to stroke volume. They rise and lower together. The same thing applies for heart rate. Cardiac output is also proportional to heart rate. So knowing this equation, it allows us to consider instances that might affect stroke volume or affect heart rate, such as hormones or exercise. Heart rate can be calculated from an EKG. It's painful to do that, but you can do it. Those little tiny blocks on the background of the EK strip down there, they represent time. Can you see that there are like thicker outlines like this one and this, right? And then there's little tiny blocks in between them. So the thicker outlines, they represent 1 second. And both of these strips, both of them, represent 5 full seconds of runtime. So my patient sat there all hooked up for just 5 seconds. All right, so on the top strip, we seem to have 6 cardiac cycles, right? We have 6 beats, and I have those 6 beats for 5 seconds. Yet nobody cares about your 5 seconds. Right? Right? Nobody cares about your 5 seconds. But what we do care about is the beats per minute. And we can do that if we say that we want this fraction here to be equal to 60 seconds. And I don't know what x is going to be up there. You get to calculate x. Interesting. So we can set up the same thing over here. So over here on this strip down here, I have 5 seconds, but I have 1, 2, 3, 4, 5, 6, 7, 8. Sorry, I probably should have counted that before I recorded this. But then that means that I have 8 beats per 5 seconds. I don't want that. Nobody cares about my 5 seconds. So I'm going to make a fraction, and I'm going to calculate x. And what this will all give me is the number of beats per minute. And that is what heart rate is calculated in, beats per minute.